Thank you. So this is work that has been carried on by Étienne André, Chapagat Bollard, Angèle Le Faucheux, and Dylan Marino, and not me. So the context of this work is to analyze attacks and see whether an attack on the system can be carried on. A timing attack, more precisely. So the timing attack is deducing private information from timing data that is given by execution time of the system. So the attacker, in that case, we are considering that the attacker only knows the execution time and the model of what can happen, but he has no information about the actions that actually happened, as you will see in some examples just afterwards. So the issues there is that, well, maybe what can happen may depend on the implementation or even on the compiler of the system. And a relatively trivial solution would be to make the program last always its maximum execution time so that an attacker cannot deduce anything from when it gets the answer. But the problem with, well, the obvious drawback with that is you lose efficiency because you are spending time waiting. So in general, the problem is non-trivial. If you consider a simple example of timing attack, just to know a bit better what we are talking about, well, this is a very trivial example. So you have a program with two inputs, one that is a password, which is a real password, and the other one is a tentative password. So the attacker is trying to guess the password. And the program is just comparing letter by letter what happens. So returning true or false. So let's look at run, where we have the real password, which is chicken, and the attempt, which will be cheese. And let us look at the execution time. So the algorithm first checks that the first two letters, well, the first letters of the both words are exactly the same. So this is C in both cases. That took some time. So here it's denoted epsilon. It took some time to check that they're identical. Then we can go to the next letter and do the same. So it takes twice the time to check the letter. And then we do it again. And the attacker can notice that I and E are different. And so after three time slots of comparisons, it can deduce that, well, we got a wrong result. So the problem here is that the execution time is proportional to the number of consecutive correct characters from the beginning of the attempt. So the attacker could say, well, okay, I waited 3 units of time, and so I know that my first two letters are correct, and the third one is not good. So this is something that you would like to avoid, because the attacker could play a game. And so informally, the problem is, can we exhibit secure execution times? And this is a problem of timed opacity computation. So we want to exhibit execution times for which it is not possible for the attacker to infer information on the internal behavior of the system. So I will first present some preliminaries on timed opacity and preliminary results on the formalism, and then the contribution of untimed control for timed opacity and some perspectives. So let's start with the preliminaries. So the timed automaton, well, I think you were all there before, so it's the same coffee machine as before, but it's a timed automaton, so there's no parameters in this case. So we have this finite state automaton with locations and actions. where you can press, you can start in the initial state, which is green here. You can press a button and you can add sugar in that blue state by pressing the button again, and eventually you get a cup and the coffee will be delivered. And here you have timing information, so timing invariance, constraint invariance. So you have a clock Y that should be less than 5 to stay in the state adding sugar, which is blue, and this Y should be less than 8 to before delivering the coffee. Okay, and guards for the transitions. So you can you have to let one time unit pass to press the button to add one more sugar, and and the clock is reset. So every one time unit you can press the sugar button, and and that's it. So so it's similar to what I presented in the previous talk. It's similar coffee machine. Okay, so this is our coffee machine. So an example of concrete run of this coffee machine is the following. So initially you're in the green state with two clocks X and Y that are 0. You can press the button and the two clocks are reset, so they are still 0. And you get in the blue state, and then maybe you can wait 1.5 time units, and you get two clocks that are 1.5 and you're still in the blue state. You can press the button. So this is possible because X is greater than 1, and then you reset X. So you get into a state where X is 0, Y is 1.5. So it's still smaller than 5. So you're fine. And then maybe you can let 2.7 time units elapse, and you get to a new state where X is 2.7 and Y is 4.2, where you can press the button again, where you reset to X, Y doesn't change. And finally, well, you can let 0.8 time units pass, and you get in a state, you're still in the blue state, but X equals 0.8, so you can't press the sugar button again. And Y is equal to 5, so you can't let time elapse anymore because Y has reached its limit. But you can take this transition cup because Y equals 5. Then you get to the red state where Y is smaller than 8. Well, it's 5, so it's okay. And there you can let time pass for 3 time units. So Y reaches 8, and you can deliver the coffee by the last transition and get back to the initial state. So this is an example of concrete run for the coffee machine. So how to formalize timed opacity? So for formalizing timed opacity, we will first consider that we have a system, so an automaton, where there are particular locations, so the initial location of 0, a final location that the attacker will be interested in, so LF, which is this one, and a special private location, private, which is the red one. So well, in general, as you will see, the automaton is larger, but you have all these characteristics: initial state, end state, and a private state, right? So timed opacity will be that the attacker, when he sees this final state, he can deduce some information that will be interesting for it. So we'll say that the system is timed opaque with respect to the private location on the way to this final location for a given duration d, if there exist at least 2 runs to this final location, and these 2 runs are of duration d, one that is going through this private location and one that is not. So basically, there will be a path from L0 to LF that will last d time units, and there will be a path from L0 to LF through L private that will have also duration d. So the attacker, when he sees, he sees the state is LF, he can't deduce whether you went through this private location or not. So he is losing some information. Okay, so let's take an example. So here we start in L0 with a clock X that is must be smaller than 3, and we can do action A to go directly to LF with when X is greater than 2. We can do action B to go through L prime when X is greater than 1, and we can stay in this private location as long as clock X is smaller than 3, and then we can exit via action C. So there exist at least 2 runs of duration D equals 2. So the first one visiting L prime. So you start in L0, then you let 1 time unit pass, so X equals 1. You're still in L0, then you can take action B because X is greater than or equal to 1. And you can do that because X is smaller than 3, it's 1. Then you can let another time unit pass, so your clock X equals 2, you're still in L private, and you can take action C and you arrive in this final location. So this is a pass of duration 2 going from L0 to LF through L prime. Then there's another pass starting from L0 going to LF without visiting the private state. And for that, while you are in L0, you can let 2 times unit pass, so X equals 2, and you're still in L0, and then you can take this action A, and you're in the final state with clock X equals 2. So in both cases, the duration was 2 time units, and what the attacker can see is that you arrived in the final state with 2 time units. So the system is said to be there to be timed opaque with respect to the private location on the way to the final location for duration D equals 2. And you can also check that it is the case for any D between 2 and 3. So for D equals 3, it's the same thing. You can construct the same kind of runs. So in between, when you're in the private location, you just have to spend D minus 1 time units. And for not visiting the private location, well, you just spend D units in the initial state. So these things are possible, and so the system is timed opaque for all durations between 2 and 3. Okay, but there is still a problem there. There exists a run of duration 1.5 that is reaching the final location, and that is visiting the private location. And this is the run. So you start from L0, you let 1 time unit pass, then you execute B, you are in the private location, you let 0.5 time unit pass, and you execute C, and you're in the final location. So here, the attacker sees that you're in the final location and you've spent 1.5 time units, but there is no such run that goes directly from L0 to LF by taking A, because the clock must be greater than 2. So there's no way to go directly to final location with 1.5 time units. So the system is said to be not fully timed opaque with respect to the private location on the way to LF. So what is, well, the computation problem here is to find the durations, the execution times, such that the system is timed opaque with respect to private location on the way to the final one, and the durations D, such that the system is timed opaque, can be efficiently computed and effectively computed and defined. The corollary is that asking if a TA is timed opaque for all its execution time is decidable. Now we can decide the computation decision problems for timed opacity, but well, that doesn't address the problem of the model not being fully timed opaque. And We would like the attacker not to get information in these cases. So to avoid not being fully timed-opaque, we want to disable some user actions to make the system fully timed-opaque by controlling some of the actions. So the goal is to exhibit a controller that guarantees the full time opacity, right? And this is by keeping a subset of the actions while the other controllable actions are disabled. So in this approach, there are two kinds of actions, some that will be uncontrollable, and they are typically actions that are required by the system or depending on another agent that is dealing with the system, and those that are controllable that we can disable. So here is another example where we start in this location L1, and we want to go through this private location L2, and the final location is here in green LS. And we have an uncontrollable transition U, which is happening from L3 to LF and from L2 to LF. And the other ones are all controllable actions that are named A, B, C, D, E, F. So the question is, first, is the system fully timed opaque? And we can see that we can go by passing by L2. We can do that between 1 and 5 time units, depending on what we are executing. And not passing by L2, we have other possibilities. So we have from 1 to 3, we have exactly 4, and we have everything that is greater than 5 that allows to go from L1 to LF without passing by L2. So this system is not fully timed opaque. Now, if we allow only transitions U and B, U plus B, so basically this path that goes from L1 to L2 by transition B, and from L2 to LF, and allow also action C, which is this one, and this is U. So we disable everything else. The difference between this and the previous thing is just that everything that is disabled disappeared, right? So you can't go from L1 to L3 or L4, so this part doesn't exist anymore. So in this system, the question is it fully timed opaque? And if you go through L2, what happens is that you spent 2 time units before taking B, and then you reset X, and you can spend up to 3 time units in L2. So between 2 and 5 time units in total, you can take U and go to LF. So if you take this path, the attacker will see you are in the final state and you spent between 2 and 5 time units. If you go directly by taking the action C, then you have to spend 4 time units in L1 and you can take action C. So you will arrive in LF exactly at time 4. So if the attacker sees, well, it is time 4, it took time 4, it can't tell you whether you went directly or whether you went through the private location. But this is not enough, because for all the other points in this interval between 2 and 5, well, the attacker can deduce you visited the private location. So this is not fully timed opaque. If you choose other transitions for the control, so if you say that you allow U and A and F, and you disable all other transitions, this is what is left. And so if you want to pass through L2, you have to take this A, and which requires X to be greater than 1. So you have spent at least 1 time unit. Then maybe you do this self loop, but you're not obliged to do it. and then you can go to LF, so that is at least 1. And if you took the self loop, then you can take 3 time, up to 3 time units to go to LF. If you go the other way, well, it's also between 1 and 3, so you can go directly from L1 to L3, and then when X is between 1 and 3, you can go to LF. So in this case, it's fully timed-opaque. So you can see that the set of allowed actions is a solution for controlling the system. And in this example, it can be shown that the set of actions to allow is either U and A, or U and A and E, or U and A and F. And well, there are 3 possibilities, and you can see that you have a minimal set of actions to control and 2 flexible sets of actions to control to ensure full-time opacities. So there is a tool that is open source, written in Java, that automates finding these strategy, and it is called strategFTO. It iteratively constructed the strategy by computing the private and public execution times using the tool imitator I talked about in the first presentation. And it checks full-time opacity by checking the equality using the polyop tool, by considering execution times as a timing parameter, and performing parameter synthesis as the things I presented in the first talk I gave. So this allowed for a proof of concept, and it was applied to a benchmark of an automatic telling machine. So you see it's a bit more complicated, and actually the secret is not here a location, but an action. So you can quite easily flip from a private location or a private action. So this tool was used on this benchmark, and it was possible for to find subsets of actions that are required or that should be disabled depending on what you want, and to synthesize a minimal controller or a maximal controller to find either one or all of them in the tool. Some scalability tests were done just by adding an increasing number of self-loop transitions, so that it's a bit artificial, but it increases the model, and to check for to check for scalability, and so you can see that it scales quite well if you want to find the minimal strategy. So perspectives for this work are, on the one hand, theory by using symbolic reasoning instead of a simple enumeration of what you can do. It's also extending the method to time control, because here you know that you can go through a path or another path, but nothing says, well, I can take this action if time is between something and something. And so time control would allow for that. And on the other hand, another perspective is algorithmic and implementation oriented. So to translate automatically some programs to timed automata and to repair a non-timed opaque system. Thank you for your attention.
Thank you. We have some time for questions. Yes.
Yes, I guess that it may be possible that there's no such self-controllable subset that is truly okay. I mean, in practice, it might be possible that for some model, there may be no such fully time-opaque controls.
It might be the case.
That's probably that you need to modify some time conditions. So how easy is that?
Well,
I don't know. Maybe Etienne is here and can answer the question. But yeah. I think that here you have a finite set of transitions. So, well, either you can, if you do enumeration, then you can see all possibilities. Yeah. So, but it takes time. So it should be decidable. But it can tell, maybe it can tell you that there's no control. Yeah, because you can test all the combinations of actions. So try to find something.
Are there cases where you can disable either one transition or another to make it work, but you cannot keep both? You know that?
Yeah, I would say so, because what you say in the end, in the beginning, is that some actions are controllable. So you can decide whether you use it or you don't use it. And there might be some, so it was not the case in the example there, but there might be some cases where you allow one transition in one case, and in the other solution, well, this transition is disabled. And it might be the case in the automatic telling machine example.
Yes, I don't remember exactly, but it looked like it. Right.
Yeah. There are different transitions to disable.
Then it could be interesting to have a notion of preference, which actions
Yeah, sure.
others. If Etienne is online, the chat definitely works, although we haven't had any messages. I'm not sure if it's possible for remote people to say something. I don't know if our speaker is connected to the input from AirMeet, but the chat seems to work. So you can also ask questions on the chat, and then we can see them.
You should close the direct messages then.
Oh, that's not the chat. That's the.
Yeah.
Okay.
It's something else.
We might be using that maybe.
Where it's
feed. Oh, okay.
Oh, okay.
Okay, and that's maybe for everything. That's not just
Close it in the top right with the X.
event feed.
Yeah.
Yeah.
Oh, okay. No, thanks,
this
Dylan.
Is Etienne.
Or Etienne using Dylan's account. Yes. Okay, thanks. So now we're getting interactive with people who are remote. Sorry that we saw the wrong chat. We were looking at the event feed, not at the workshop chat until now. But for the remaining sessions today, we know where to look. It's almost every event is a different online tool, so it's a learning curve every time. Okay, we have time for one more quick question, if there is one.
I have a question. This is probably me misunderstanding timed automatons, but you had entered these self transitions, right? Wouldn't it be the case that you always want a self transition for every state?
Not necessarily.
Okay, because I'm just thinking in some example where you step some very small delta of time. You want to be able to represent that, or do you restrict this?
No. In fact, the time passing is inside the location. It's not represented on the arcs.
Okay. Oh, I see.
So it does what you are asking for.
Yeah.
Without having an arc outside.
I
So
see.
you are in the location and you say, well, time passes, and I let that amount of time pass.
Okay, so some implicit. Yeah, I see. Thank you.
Okay, then let's thank the speaker again.